let's talk about differential equations. This is going to be like a mini course on the first order differential equations. And before we get into it, let's talk about what is a differential equation in the first place. So a differential equation is basically a way to model how a specific function or, a set of functions, how do they, change over time. So let's say I have something like dy over dx, and let's say that's equal to 2. Okay, this is just saying that, well, whatever function we have, f of x is equal to something, right? Whatever function that we're talking about, well, the rate of change of that function is going to be equal to 2. And it's actually, in this case, it's actually going to be independent of the x and a y value. So for any x, y value that's inside our function that we're looking at, the slope of our function is always going to be 2. So for example, one example of a solution to this differential equation would be 2x. F of x is equal to 2x. Because, well, what is this? This is the equation of a line in the xy plane, right? And of course, well, that is pretty badly drawn. And of course, this is going to have a slope of 2, right? Because it's a line. The slope is constant, which is what this differential equation is saying. But another solution that I can have is, well, 2x plus 1. Because this plus 1 right over here is just the y-intercept. So it has no effect on the slope. And it turns out that I can do 2x plus 2, 2x plus 3, whatever, 2x plus 4, 2x plus a million. It doesn't matter, right? And so the way we would express the solution to this differential equation is, okay, I know that the slope has to be, has to involve 2x in here, right? Because it's a line, right? The slope is constant. And then I'm just going to add an arbitrary constant at the end, plus c, to indicate that, well, this is kind of like our y-intercept. It's just a constant. It doesn't affect the slope. So let's talk about separable differential equations. And a separable differential equation is basically when you're able to separate the x's from the y's. So if I have dy over dx, and let's say that's equal to xy, right? Yeah, I want to get all the y's on one side and all the x's on the other side. That is like the simplest case. So what I can do is I can divide both sides by y, and I multiply both sides by dx. So dx times dx, I'm just going to get x dx on the other side, right? I divide by y on both sides, and I multiply by dx on both sides. And so separable differential equations is when you can get all the y's on one side and all the x's on one side. And the general form for this is you have dy over dx. It's going to be equal to some function of x, which I can say this is f of x, right? So in this case, f of x would be this. X right over here is some function of x. And this f of x is going to be multiplied by some function of y, which I can say this is going to be g of y, right? Because g of y would be this y right over here. And I'm able to separate the function of x from the function of y, which we see right over here. And so to solve this, well, you got to use some of your calculus skills, some of your integral skills. We integrate both sides. Well, the integral of 1 over something, well, with respect to that some variable, well, that's going to be ln of the absolute value of y, right? And the integral of x is just x squared divided by 2, and then don't forget the plus c. Okay? And so we can solve for y. We raise both power to e, right? So I get y is going to be equal to e to the x squared over 2 plus c. Don't forget that everything is still raised to the power of e here, right? So it's e to the power of x squared divided by 2 plus c. And recall back to your exponent rules, right? When you have a to, let's say, the power of x plus y, that's equal to a to the x times a to the y. So this right over here, e to the x plus 2, e to the second power divided by 2 plus c, well, that's just going to be e to the x squared over 2 times e to the c. All right, so this is using the exponent rules. We can do that. Now, e to the c, well, c is a constant, right? This right over here is a constant from our integration. So e to the c is just going to be another constant, right? For example, if c was equal to 3, let's just say e to the 3, that's still going to be another number, right? Another constant. And so if we let, let's say c1, let's just let c1 be equal to e to the c. We set another arbitrary constant equal to this constant that we have here, just to simplify things a little bit. And so our final our final simplified equation is going to be C1, which we know is this, multiplied by e to the x squared over 2. And that is going to be the solution to this. All right. And notice how the C1 right over here, that kind of represents, like in our original example that we saw before, that kind of represents like the range of possible solutions that we have to our differential equation. Remember that these type of equations, a lot of times they don't have just one solution. They have infinitely many number of solutions, right? And so this C1 basically encapsulates, I guess it can say, like the set of all functions, or like just like the range of all functions that satisfies this equation right over here. Now, let's say that we were given an initial condition. All right. So let's say that this is like the range. This is like the range of all the functions. But the range of all the functions that satisfies this differential equation right over here. But what if we were given an initial condition? What if we said that f of 0, let's say that was equal to 3. So this right over here is an initial condition, and it limits the range of our set of all the possible solutions to this equation. And so what do we got to do? How do we find the equation given an initial condition? Well, let me just replace this y here with f of x. So let me just, whoa, I don't know how to change. Oh, there it is. So I'm going to replace this with f of x. And so we know that f of 0, so when we plug in an x value of 0, we get a y value of 3, right? That is our y value. If you're given an initial condition, all you got to do is you plug this x and y value back into our function, and then you just solve for the constant. So we know that we plug in 0 in for x, right? So we have c1 times e to the, instead of x here, it's 0, right? So 0 squared is just 0, and 0 divided by 2 is still 0. And we know that whatever this side is equal to, well, it has to be equal to f of x. And, well, from this initial condition, we know that that has to be equal to 3, right? So it's just plugging, chugging, and we know that e to the 0 is 1. That means that our constant has to be equal to 3. And then so, you know, if we were to solve for that specific function that satisfies this initial condition, well, then c1 would just be equal to 3. So our final equation would be 3 times e to the x squared over 2. So initial conditions, most of the time, you know, they're just going to limit your solution set down to just one single function. But, you know, the steps remain the same, right? You just solve the differential equation first. And then once you get your function in terms of, you know, whatever constant that you have, you just plug in your initial conditions into that function, and then it'll kind of narrow down into that specific function, okay? Linear differential equations are pretty cool. So they're going to be in the form of dy over dx plus some function of x, which I can say p of x, right? P of x times y is equal to another function of x, q of x, okay? So for example, dy over dx is equal to, I don't know, 3x times y plus, I don't know, like 5x squared, right? That would be an example of a linear kind of equation, okay? And so the intuition behind linear differential equations is you want to somehow turn this side of the left-hand side of the equation into some kind of product group. All right, so I want to write this as the derivative of a product, some product, right? And then that's going to be equal to whatever the right-hand side is going to be equal to, right? So q of x times something. We don't know what that something is, right? Times something. And then, so the thing is, you want to turn the left-hand side into a product because, you know, you have a dy over dx here and you have a y here, and you can't really separate them, right? Because, well, you have a p of x here, right? You have a function of x here, so you can't really separate it. And so you want to turn the left-hand side into a product so that, well, now you have everything wrapped into a nice d over dx. You integrate both sides. That kind of just cancels out, right? And so you're just going to be left with the product is equal to the integral of q of x times that something that we want to multiply by, and then, you know, you'll get your solution there. But how can we turn the left-hand side of our equation into some kind of product rule? All right, how can we do that? So let's start out by multiplying the whole equation by some function. All right, we don't know what that function is. but I'm going to call it u of x. So we're going to get u of x times dy dx. Actually, I'll do the regular functions in white because that really emphasizes everything. And it's going to be plus u of x times p of xy is going to be equal to q of x times u of x. Now this is where it gets kind of weird, okay? Because what we're going to do is we want a product rule, right? And so what if I had something like u of x times y, and then I do the product rule of that? What am I going to get? Lefty right, so it's going to be left times the derivative of the right, which is the derivative of y is just dy dx, plus right, which is y, times the derivative of the left, which is u prime of x, right? So this left-hand side and this product that I wrote right over here, they look pretty similar. And if I set them equal to each other, then I'm able to find this mysterious function that I need to multiply the whole equation by that's able to allow me to turn this into a product, okay? So the point here is I multiply by some mysterious function, and in order to find out what that mysterious function is, well, I have to set, these two equations equal to each other, right? That's the only way that I can find out what this function is, right? Because I want to turn it into a product rule. And so if I set this right over here, let me just select all. If I'm able to select, I copy, paste. Wow, that's pretty cool. Okay. I'll set these two things equal to each other. Notice how this first term just completely cancels out. So we don't even need to do that, right? We don't even need that first term because it just cancels out. And guess what? We also don't need the y's, right? Because we could just divide by y on both sides, assuming it's not equal to 0. Right? And then so we just end up with, well, u of x times p of x has to be equal to u prime of x, right? After some simplifications. And we can solve for u of x. And the way we do that is, this is also a differential equation. Look at that, right? So, just to maybe simplify things to make you guys, a little bit happier, I can just write this side right over here as the derivative of u with respect to x. And then this is just going to be u of x, right? And so I can multiply both sides by dx. So I get p of x dx. And that's going to be equal to du, or actually, yeah, I'll divide both sides by u of x. Right, I get all the u's on one side, and I'll get all the x's on one side. So I'm just going to get p of x times dx. That's going to be equal to 1 over u of x. I'm just going to write 1 over u, and then it's going to be multiplied by dx, or du, sorry. And so if we integrate both sides, right, well, I'm going to get that the ln of the absolute value of u, right, because the integral of 1 over something, or 1 over u in this case, is going to be equal to ln of the absolute value of u. And that's going to be equal to the integral of p of x dx. And so if we want to solve for this mysterious function u that we want to multiply the whole equation by, well then, if I take e to both sides, well then I get that this mysterious function u has to be equal to the integral, or e to the integral of p of x dx. All right. So the mysterious function that we have to multiply by in all, first order linear differential equations is going to be equal to e to the integral of p of x, which, recall that it's this function right over here, dx. And this is actually something called the integrating factor, which I'm going to write as if. Integrating factor. Let's solve one of these equations. This looks pretty fun, this integrating factor part. So I'm just going to leave that formula at like the edge of the screen, and then let's just solve one of these equations. So let's just say that y prime plus 4y is going to be equal to e to the negative x. Okay? So in this case, it looks like my p of x, right? My p of x function is just going to be 4, right? P of x is just going to be equal to 4. So e to the integral of 4 dx, well, that's just going to be e to the 4x, right? So my integrating factor is just going to be e to the 4x. And that is the quantity that I multiply this entire function by. So what do I get? I get y prime times e to the 4x plus 4y e to the 4x is going to be equal to e to the 3x because of exponent rules, right? Just add them up. And so notice how we can actually write the left side as a product rule. We can actually write it as e to the 4x times y. And if we take the derivative of that, so the derivative of that with respect to x, that's actually going to be the left-hand side of the equation written as a product rule, right? Remember back to when we did the proof. To find the integrating factor, what we had to do is we assumed that we have like a product rule where it's u of x times y, right? And we want to write it as a singular product rule. So here we have it, right? We have some integrating factor multiplied by y, and that we take the derivative of that, and that's going to be equal to whatever's on my left-hand side right over here. And so you can actually compute the derivative, if you wanted to, and you'll actually find out that's equal to this left-hand side right over here, okay? And so if I take the integral on both sides, well, I just get that e to the 4xy times y is going to be equal to, well, what is the integral of this? That's just going to be 1/3 e to the 3x. Don't forget the plus c. And then, so if we divide both sides by e to the 4x, I get y is equal to 1/3 times e to the negative x plus c e to the negative 4x, right? Dividing by e to the 4x is the same thing as multiplying by e to the negative 4x, because the exponents, they just cancel out. So that's why I just wrote it like this. But you could have also wrote it in the denominator, but here is the solution to that type of equation. And of course, if we were given an initial condition, just plug in the x values, that's going to be equal to some y value, you solve for the constant, and so on. The important thing to know about the integrating factor is that it's equal to e to the integral of p of x dx, and you're able to write it as a product rule. So that integrating factor multiplied by y, you take the derivative of it, that's going to be equal to your entire differential equation multiplied by that integrating factor. Now let's talk about substitutions. So there are certain differential equations where you might have to substitute a certain value v. So I like to call it v sub, kind of like u sub, because you kind of have to substitute in a variable, which I'll just say v. And let's see what I mean by that, okay? So let's say that we have something like, let's do something simple, dy over dx. Let's say that's equal to x squared plus y squared divided by x squared, okay? The important part to know about v sub is that you're able to turn what looks like to be a not separable differential equation, and you're able to turn it into a separable one. So this is actually the first case to look for. The first case of v sub is that you're able to turn it into a separable differential equation. There's actually a second case of v sub where you're actually able to turn it into a linear equation. That's going to be Bernoulli type of differential equations. We're going to talk about that after this, but this is the first type. All right, it's going to be you're able to turn differential equations that look not separable into one that is separable. So how are we going to do that? First, let's actually go ahead and separate this fraction. So I can say that dy over dx is going to be equal to 1 plus y squared over x squared. All right, I just separated out this fraction. Now, what I'm going to do is I'm going to let v, all right, v be equal to y over x. A big sign that you should do v sub in order to turn it into a separable type of diff EQ is when you have some function that kind of looks like f of y over x. That is a very big hint that you should be doing this, okay? So I'm going to let v is equal to y over x. And so that means that y is going to be equal to vx. And if I take the derivative of both sides, I get that dy over dx is equal to, well, this is just going to be a product rule, right? Because remember that v is going to be like a function of x, right? So v is based on the value of x, meaning that it's a function of x. So this just becomes a product rule, right? So I'm going to have v times the derivative of x, which is just 1, and it's going to be plus the derivative of v, which is just dv over dx, x. Okay. And so let's just substitute everything in here. So I substitute dy over dx into my equation. And so just copy and paste. This is pretty amazing technology right here. Just copy and paste that. And this looks pretty messy. Is there any way I can simplify this? Well, we substitute dy over dx in terms of v, dv over dx. How about we substitute in for this term as well, right? We also, not only do we want to substitute in for dy dx, but we also want to substitute in for the other xy terms, right? Especially as y squared over x squared. I wanted to get rid of these y's and get everything in terms of these v's. And so imagine if v is equal to y over x, then v squared is equal to y squared divided by x squared. Oh, wait, that's right over here. And so this is just going to be v squared. And then after that, you could just do the thing where dv over dx times x is equal to v squared minus v plus 1, right? And then let's just try to get the x on one side, and let's try to get all the v's on the other side. So I can divide both sides by this annoying term right over here. So I can get that dv over this entire term right over here. Copy, paste. It's pretty good. And I can say that's equal to, and then if I multiply by both sides by dx, I guess I can multiply both sides by dx, and I divide by x. Well then, notice how I have turned this into a separable differential equation, right? Multiply both sides by dx, you divide by x, that gets all the x's to this side, and if you divide by this entire term, that gets all the v's to one side. And then so you would actually be able to integrate this, and I'm gonna leave it to a challenge to y'all, okay? And quick little hint, I'm pretty sure you need arctangent for this one, and so yeah. But the point is that you should be comfortable in doing v sub, in which v is equal to y over x, and you're able to sub in dv dx, and you're able to sub in for y over x, and so everything is nice. All right, so the second type of v sub converts some differential equation into a linear type, in which you have to do the integrating factor. And so that type is going to be in the form dy over dx plus p of x times y is going to be equal to q of x times y to the n power. And the v sub that you want to do for this is going to be v is equal to y to the 1 minus n. This is the substitution that is important to know, okay? So let's do an example. Let's say that I have dy over dx. So I'm going to, once again, sorry if I'm moving around a little much. I'm pretty excited about this. So dy over dx is going to be an amazing example. And let's say this is going to be plus y. And let's say that's going to be equal to y to the second power. Now, if you don't see any x's, well, then you know that there's like this invisible 1 in front of these y's. And so p of x and q of x in this case, well, they have to be just equal to 1, right? And so, well, we have this y squared term. And so we know that from our v sub right over here, we have to let v is equal to y to the 1 minus that power, which in this case is 2. So v is equal to y to the 1 minus 2 is -1, okay? And so, once again, we do the same thing, right? What is dv over dx? And then from implicit differentiation, you might remember that this is negative y to the negative second power times dy dx. This is why it's important to know your implicit differentiation. And so we can just substitute dv over dx into this by dividing both sides by negative y to the negative second power. And so when we do that, we divide by negative y to the negative second power. This cancels out, and I just get that dy over dx is equal to negative y squared dv dx, right? So let me just get rid of all of this. So that is the equation that basically remains. I wish this whiteboard would actually select everything, and I selected everything. Okay, let's just substitute everything in here. So I have negative y squared dv over dx plus y is equal to y squared. Oh, I have a factor of y in all these terms. How about I make my life simple and I just divide by negative y squared, right? Because in order to turn something into a linear differential equation, well, we have to have this dy over dx, or in this case, dv over dx. We want to have it without anything, in the front, right? We just want it naked. And so if I divide both sides by negative y squared, I get dv over dx, and it is going to be minus 1 over y. And that's going to be equal to, well, negative 1. Okay. All right, this looks good. And so now, notice how this is actually a linear differential equation. This right over here is a linear differential equation. And sorry. One more thing we have to do is we want to get everything in terms of v's and x's. We want to get rid of this y. And so recall that v was equal to y to the negative first power. So we actually can sub in v in for this term. Sorry about that. Yeah, but just like a reminder that when you're doing v sub, you want to get rid of all the y's. You want to get all the x's, all the v's. All right, that's what you want. Okay, that was quite a lot. Remember the integrating factor? Let's do that. So integrating factor, I'm just going to write it on this side. That's going to be equal to, call e to the integral of p of x dx. Too lazy to write out dx. And so my integrating factor in this case is going to be, well, negative 1, right? Negative 1. Don't forget to include the negative, all right? This is going to be equal to e to the integral of negative 1 dx, which is just going to be equal to e to the negative x. And once I actually multiply both sides by e to the negative x, I get an e to the negative x dv over dx minus e to the negative x times v is going to be equal to negative e to the negative x. And notice how this is a product rule right over here. Once again, when you're dealing with integrating factors, you should always end up with a product rule. This product rule, remember, the product rule that you always end up with is that integrating factor multiplied by y, and you take that d over dx on it, right? That's a product rule form that you always end up with. And so what is this going to be? Well, this product rule is just going to be the derivative of, well, e to the negative x times y, right? And so that's going to be equal to, well, negative e to the negative x. We integrate both sides, and we get that e to the negative x times y, or sorry, v. I'm so sorry, guys. Wrong variable. That's v. All right. That's going to be equal to the integral of e to the negative x, and the integral of e to the negative x, or sorry, negative e to the negative x. That's just going to be e to the negative x plus c. And so if we divide both sides by e to the negative x, and actually, let's just leave it as is. Let's actually leave it as is. Because what we're going to do now is we have everything in terms of x's and v's. But remember where we came from originally. We came from a world with x's and y's. And recall that v was equal to, well, 1 over y, or y to the negative first power. So this is actually e to the negative x times 1 over y, right, is equal to e to the negative x plus c. And if I multiply both sides by y, I get e to the negative x is equal to y times e to the negative x plus c. And so if I divide both sides by this term right over here, I get that y is equal to e to the negative x divided by e to the negative x plus c. Let's see. Or an equivalent form is equal to 1 over 1 plus c times e to the x. You could have actually divided both sides by e to the x, and you would end up with, this version. They're all equivalent, all right? But this right over here is going to be the answer to our Diff EQ. Let's move on to the next slide. Let's talk about autonomous. Let's talk about autonomous differential equations. Autonomous. All right. And autonomous differential equations is basically when you have something like y prime is equal to f of y. So you're basically saying that the rate of change of your function with respect to x, so dy over dx, that's going to be equal to some function of y. So let's just say dy over dx is equal to, I don't know, 2y. So notice how this differential equation does not depend on x, right? So if I were to, let's say, draw a graph of this, and let's say I want to model this differential equation, how would this look like? Using, slope fields and all that. Well, let's say that y is equal to 1. So if I plug in 1 into y, I get a slope of 2. And notice how the differential equation, once again, it's autonomous. It's only a function of y, meaning that the slope does not depend on the x value. It's only dependent on the y value. So in fact, for all x's ranging from, everywhere, all real numbers, the slope is always going to be equal to 2 if the y value is equal to 1, right? The slope is always going to be equal to 2 when the y value is equal to 1. If we have, let's say, y is equal to 5, well then 2 times 5 is 10. And so, well, the slope is always going to be 10 at y is equal to 5, right? It's independent of the x-axis, right? And in fact, what, a lot of times what we do is we actually don't need the x and y-axis because the differential equation is just dependent on one variable, right? So sometimes what we might do is we might have a number line, right? It's just a single y-axis, and we use that to actually model our differential equation. And there's actually something called equilibrium points, which I'm going to get into shortly. But autonomous differential equations, let's just first talk about how to solve them. Well, autonomous differential equations, notice how they're separable. I just divide 2y on this side into this side. I multiply this side by dx, right? So let's just do a quick little separable differential equations practice. So if I divide both sides by 2y, and then I set that equal to dx, right? Then I integrate this, I get that x plus c is going to be equal to, well, we might need to do a u sub here, right? Or, you might already know this by now, but let's just do this real quick. So let's let u is equal to 2y, and du is going to be equal to 2 times dy. So du over 2 is equal to dy. And so let's substitute everything in. So I get that this is the integral of 1 over u. And we know that dy is going to be equal to du over 2. And so we can factor out the 1/2 from this. And so what we actually get that x plus c is equal to 1 over 2 times the natural log of the absolute value of, well, remember where we came from, right? This is going to be the absolute value of u, but we know that u is equal to 2y. So it's just going to be the ln of the absolute value of 2y. And so we multiply both sides by 2. And we raise both sides to the power of e. So we actually get that 2y is equal to 2x plus 2c, and all raised to the e. Right? Notice how this plus 2c right over here is just going to be another constant, like we said earlier in the video. Let's just call this big C. And then we divide both sides by 2. So we get that y is equal to all of this divided by 2. And there is going to be our solution. And actually, a simpler way I could have done this was probably just, I could have done, let me just do it the second way for more practice. So dy over y is equal to 2 dx. I probably didn't have to divide by 2, and it probably would have been simpler because this is just a simpler integral, right? This is just going to be ln of the absolute value of y is going to be equal to 2x plus c, and then we raise both sides to the e power, no need to u sub. And so we get that y is equal to c times e to 2x. But, I mean, we get the same answer either way, because this is actually pretty cool, because guess what? I can write my first answer as just y being equal to c1 over 2 times e to the 2x. And notice how c1 over 2, that's just going to be another constant, which I can write as c times e to the 2x. So these two answers are actually the same, because sometimes it's a little weird, you might find that there's multiple paths to the same answer, but at the end of the day, they're all the same because sometimes constants can be, they can absorb, numbers because that gives you another constant, right? So that's actually pretty cool. So let's talk about equilibrium points. So we're going to dive deeper into first order autonomous differential equations. And so what you notice is if I draw the entire slope field for this differential equation, right? dy over dx is equal to 2 times y. Let's say that y is equal to -1. Well, then -1 times 2 is -2, so it's going to have a -2 slope all throughout this, right? And all throughout the x values. And then let's say another one, -5. -5 times 2, -10, so it's going to have a steeper negative slope all throughout y is equal to -5. So notice what's going on, right? Notice how it looks like all the points are sort of diverging away from y is equal to 0, right? So at y is equal to 0, this line right over here is y is equal to 0. It looks like the points are sort of diverging away from it, right? And when the slopes kind of diverge away from an equilibrium point, so y is equal to 0 is an equilibrium point, right? So this is actually an equilibrium point, you would say. And the way you find equilibrium points is you just set this to y, you just set the differential equation equal to 0. And so in order for this to be equal to 0, well, then the y value has to be equal to 0. And so if we focus on an equilibrium point and we see that the slopes kind of diverge away from it, we would say that's an unstable equilibrium point, okay? So above or below the equilibrium point, an unstable one, it would be the slopes diverging away from it, okay? And you might guess that a stable equilibrium point, you kind of have the slopes converging towards it, okay? And so let me just pull up a simulation real quick. So right over here, I have the equation dy over dx is equal to 1 plus y times 1 minus y, and let's add a 1 minus, I don't know, or 2 minus y, all right? Let's add that, okay? And so I can kind of click on the graph and it will kind of add like functions, all right? Because remember, for differential equations, there's like kind of an infinite amount of function solutions. So by just clicking on an initial point, we're able to have a function that kind of this differential equation will map to, okay? And so I'm just going to click around on this point and I'll send you guys the link to this, simulation in the description. But I want you to notice what's happening, okay? I'm just going to click around a bit and hopefully a trend starts to appear. Okay, you see it? So let's take a look at some of the equilibrium points. So equilibrium points, once again, is just when this differential equation that's in terms of y only, you set it equal to 0. So at what points is this equal to 0? Well, let's take a look at the first case when y is equal to -1, right? Because it looks like with -1, there's a slope of 0 here. Notice how the points kind of diverge away from -1. So at y is equal to -1, you have an unstable equilibrium point, right? You diverge away from that as, you tend towards infinity, right? Let's take a look at the next one. Let's take a look at when y is equal to 1, because when 1 minus 1 is just 0. So at y is equal to 1, notice how the points kind of converge to it as your independent variable approaches infinity. And so it looks like that at y is equal to 1, you have a stable equilibrium point. Now let's take a look at the final example, where y is equal to 2, right? Because 2 minus 2 is 0. At y is equal to 2, notice how the points are diverging away from 2. So y is being equal to 2 would be an unstable equilibrium point. And so let's take a look at how we can determine this algebraically. So we learned how to determine stability kind of from the slope field, but now let's determine the stability from an algebraic perspective. So I have to look at the graph one more time. So this is 2 minus y, okay? This is very similar to critical points that you've dealt with, right? When you're doing, analysis of graphs. So we have a equilibrium point at 2. We said there was one at 1, and then there's an equilibrium point at -1. So we just have to kind of plug in points from each region and see, their behavior. And so take a look. If I plug in -2, well, -2 that's going to be -1, right? Because 1 plus -2 is -1. If I plug in -2 here, I get a negative number. And if I plug in -2 here, I get a positive number. And so it looks like that kind of, oops, this is actually positive, sorry. All right. Once again, if I plug in -2 into all the y's, right, so some number in this region that's below -1, well, then I get a negative number here, right, because 1 minus 2 is just -1. If I plug in -2 into this y, I get a positive number, and same for the last one. So overall, my slopes are going to be diverging away, right, because imagine if you're at -1 and your slopes are negative, right, your slopes are going to be negative, so you're going to be kind of diverging away from -1. And notice how, once again, we only have to represent everything with one axis because an autonomous differential equation only depends on the y. Let's plug in a value between 1 and -1. Let's say 0, all right, to make our lives simpler. So I get 1 times 2. Oh, it's positive. So from this region, from -1 to 1, our slopes are going to be positive. Let's take a look at this region right over here. Let's plug in like a number like 1.5. So this is going to be positive. 1 minus 1.5, that's going to be negative. And 2 minus 1.5, that's going to be positive. So it's going to be downwards like this. And let's plug in a number that's bigger than 2. So let's say that this is going to be positive, right? A number like 3, right? So 1 plus 3, positive. 1 minus 3, that's negative. 2 minus 3, that's negative. Negative makes a positive when multiplied. And so overall, the slope is going to be positive. And so take a look at what happens. When your points are diverging away from that equilibrium point, 2 looks to be unstable because it's diverging away from it, right? At 1, right over here, the points are coming towards it. So this is going to be a stable one, right? Because the slopes are converging towards it. And for -1, the slopes are diverging away from it. And this is going to be unstable. And if we, once again, look back at the graph, this confirms it, right? 2, it's going to be unstable. 1, it's stable because it's converging towards it. And -1, it's also going to be unstable because it's diverging away from it. And so this algebraic idea of equilibrium points and all of that, right? This is the way to do it. You draw a number line, and then what these answers basically tell you is that for unstable equilibrium points, kind of like a more formal definition of it, is that actually, let's start out with stable points, okay? So for stable points, as your independent variable approaches infinity, right, your solutions that are near this equilibrium point get closer and closer to it. For unstable equilibrium points, as your independent variable, so x, approaches infinity, solutions near this value are going to leave it. So they're going to diverge away from it, okay? It could be towards infinity or it could be towards another equilibrium point, but the point is that it diverges away from it. So that is kind of like the more formal definition of all that. Finally, let's talk about exact equations. So exact equations, they're in a form of, it's typically written as m of x comma y dx plus n of x comma y dx, or sorry, dy. That's going to be equal to 0. And this is kind of a moment where you have regular calculus, all right, so like calculus you learned, for Calc 1, and that's going to intersect with Calc 3, all right, multivariable. And so let's say that I'm going to work a little backwards here, but let's say that I have a function like a multivariable one. So I'll call that multivariable functions. They receive 2 inputs, right? So instead of just f of x, you have f of x comma y. And let's say that's equal to this x squared y. Let's just say plus y squared. Let's just throw in 3x there, right? This is how the multivariable function would look like. Now let's just set all of this equal to 1. So what does that actually look like? Okay, so I'm actually pulling up Desmos 3D right now. So x squared y plus, y squared plus 3x, okay? And so this is kind of what this function looks like in 3 dimensions. And then if I set that equal to 1, this is like the slice of that function. So you can see that this is my original function, right? And then if I just kind of slice through the function in which, the height of the function is equal to 1, because for 3-dimensional functions, right, you have some input x comma y, and then the output z, which we call that represents the height of the function. So when I have x squared y plus y squared plus 3x is equal to 1, I'm trying to see all the points on the function where the height is equal to 1. So I'm kind of taking a slice out of the function for where the height is equal to 1. And if I were to do that, well, then you would get this portion, right? Okay. Now, normally, if I want to differentiate this, so forget this f of x comma y part. If I normally want to differentiate this with respect to x, well, let's review kind of implicit differentiation real quick. So derivative of constant is 0, and so I get the product rule for this. So left d right plus, and then right d left. So right times the derivative of the left, so 2xy. And this right over here is once again another chain rule. And then this is going to be plus 3 is equal to 0. And so if I move all these non-dy dx terms to one side, I get negative 3 minus 2xy. And then if I factor out a dy dx from both these terms, I get that negative 3 minus 2xy divided by x squared plus 2y. That is going to be my differential equation, okay? Now you said, oh, wait, but doesn't exact equations have to be in this form? And you're completely right. What I can do now is imagine if I multiply both sides, like cross multiply everything, right? The butterfly method. So I get x squared plus 2y times dy, right? And it's going to be equal to, and on the opposite side, I'm going to have negative 3 minus 2xy times dx. And so if I subtract this term to this side, so if it's going to subtract this term right over here, this side, right, and I set that equal to 0, well then, would you look at that? I have some function here, which I call m, that's a function of x and y, dx, and I have plus the other function, right, in this case it's a minus, but here you can think about it as plus negative of whatever is in here, right? This function is going to be n of x comma y. This function is m of x comma y, right? And it's all going to be set equal to 0. So make sure that if you're asked to like differentiate this function and then you're asked to place it in this exact equation form, you know how to do it. All you have to do is just cross multiply once you get into this dy over dx form, and then you should be able to end up with this, perfectly, okay? To understand this, we have to look at something called the total differential, okay? And the total differential is going to be describing, well, how much does our function change in its height when we move a little bit in the x direction and a little bit in the y direction at some point, okay? And the total differential is described by essentially the slope of our graph, or the slope of our function when we move a bit in the x direction, times the tiny change in x that we actually make, plus the slope of our function in the y direction, times the tiny change in y that we make. And if this is still confusing, well, we can always simplify things down, right? Once again, let's just go back to the 2D axis, right? X and y. Let's say this is the graph of y is equal to 2x. Now, if, let's say I start at the origin, and let's say I move 2 units to the right, what is going to be my new height? What is going to be my new height? Well, if I plug 2 into my formula, I get that y is equal to 4, right? So my new y value is 4. Notice what I did here, right? If I want to get a tiny change in y, right? If I'm looking for a tiny change in the y value, right, which is represented by this, right? This is a tiny change in my y value. What do? I multiply a tiny change in the x value by the slope, right? In this case, the slope is 2. This is the same concept that we're seeing here. To find the change in the total height of the function, I just multiply the slope with respect to that one variable, because this is multivariable now, right? I multiply the slope with respect to that variable times the actual tiny step that I took in that direction. And I do the same thing for both axes. And so this is the same concept, right? Okay, good. We have that established. Now we know that, this total differential right over here, it's going to be equal to 0. Why is that? Well, remember back to the original equation that we have. We're basically saying that our multivariable function right over here is equal to a single value. It's equal to a height of 1. If a multivariable function is equal to the same value, that means that the change in the height, right? You can think about this as the height. If the height is always constant, there is no change, right? df would just be equal to 0 because there's no change to the height. And so this right over here is the idea that links it all, okay? Because look at what happens when we actually compute this. So what's the partial derivative of f with respect to x? Sorry, I forgot to put the 1 there. So the partial derivative of f with respect to x, well, you would just kind of differentiate this as normal, but you would keep y. You would treat y as a constant. So this would just be 2xy plus 3, right? You treat y squared, or any y's, as a constant. So, derivative of a constant is just 0. And you multiply that by dx. And likewise, you add this to, well, the partial derivative of f with respect to y. And so that means that, well, we treat x as a constant. So this right over here would be a constant. And you would just get x squared plus 2y, right? And then this would be multiplied by dy. And you would set that equal to 0. Take a look at what we have. This is what we have here. And then this is what we have down here. These are actually the same thing, right? Because if we divide both sides by -1 here, I get that 3 plus 2xy dx. And then this negative cancels out, so it's going to be plus x squared 2y dy is equal to 0. And so this is a very, very powerful idea. The total differential, right, if we relate this to three-dimensional calculus, is actually the same as if you did the implicit differentiation in the 2D world and you got it into this form, right? And I don't really like the partial, derivative symbols because they kind of make things confusing. So I'm just going to say that the partial derivative of f with respect to x, let me just call that f and like a subscript x. And likewise, the partial with respect to y is going to be fy, okay? And recall that our total change, we set that equal to 0, right? Because our multivariable function is constant, right? We're setting it to some constant. And so if I want to isolate dy over dx, well, what I can do is I can subtract f of y. So f subscript y dy is equal to, I know it's partial with respect to x, but y over dx is going to be equal to the partial with respect to x divided by partial with respect to y, and we have the negative sign in front, okay? Now, let's take a look at what happens if we try to do this with the chain rule. So once again, we have a multivariable function. In this case, for our example, this is equal to 1. And let's try to differentiate both sides with respect to x. So of course, on the right-hand side, we get 0. And on the left-hand side, well, we're just going to get the partial derivative with respect to x plus, and because y is a function of x, we can use the chain rule, right? And so this just becomes the partial with respect to y times dy over dx, right? Times dy over dx, because this is just using the chain rule, right? If we want to differentiate y, well, it's just going to be whatever, we kind of treat y as, the outer function. We differentiate it like normal, and we multiply it by dy dx. And so once again, if I want to isolate dy over dx, I move this to the other side, so I get negative of the gradient of x, or so I get, negative the partial with respect to x divided by fy, right, partial with respect to y, and that's equal to dy over dx. And you can see that both ways, either way that I view this, I get the same answer. So now that we get how the total differential and essentially the chain rule, how they're equal to each other and they give us the same answer, let's try to work backwards now. So what if we were given this right over here and we were trying to find out our original function, which is this? Then this original function we said was f, right? This is our multivariable function that we want to find out. So I'm going to delete all of this. And let's see if we can try and work backwards. So recall this form of, the differential, right? We say that, well, we have it up here, right? This is going to be the partial of f with respect to x times dx plus the partial with respect to y times dy. Now, if these forms were matching, right? These forms are matching each other, right? Meaning that partial of f with respect to x has to be equal to this term, right? They have to be equal to each other because, they're in the same form and everything, right? So I could just set partial of f with respect to x is equal to 2xy plus 3. And what I can do is I can integrate this with respect to x, right? So I multiply both sides by dx. And so what I get, well, I get f, my original function, right? I want my original function back, f, right? That's what I'm looking for, okay? And in order to integrate this with respect to x, you treat y as a constant. So this is just going to be x squared y, right? And then this is going to be plus 3x and a constant. Now this constant right over here, this constant is actually going to be a function. All right. Now why is that? All right. So instead of getting a regular plus c like we usually do, we actually get a function that is in terms of y. Why do you think that is? Take a moment to think about that. Well, if we have something, if we have a partial derivative with respect to x, right? We want to find out a partial derivative with respect to x, right? Let's say if I have the function f is equal to y. If I take the partial derivative of f with respect to x, notice how y is just treated like a constant. So this is just going to be equal to 0. Any function of y, where I'm taking the partial derivative with respect to x, is just going to get zeroed out. And so if we want to do the reverse, if we want to integrate this, well then I have to account for the fact that there can be a plus a function of y, right? So now that we have that established, we want to find out this constant, this function, sorry, which kind of acts like our constant. So what are we going to do? We have our partial with respect to x, right? But now let's try to find the partial with respect to y, because we know that it has to match up with this form. So if we do the partial of this with respect to y, right, on both sides, I get that the partial of f with respect to y is going to be equal to x squared plus, and then this is just treated as constant, right? And then f prime of y. And so notice how it matches up, right? These forms, they have to match up, because at the end of the day, this is a partial with respect to y. This is the partial with respect to y. They have to match up, right? This is the cool part now. We are getting to the cool part, and this is all going to make sense. Okay. So know that these have to be equal to each other. So what does f prime of y have to be equal to? F prime of y has to be equal to 2y, right? That's the only way that this can make sense. Now recall what we're solving for though. Remember, f is equal to x squared y plus 3x plus f of y. But right now we have f prime of y. So once again, we have to do another integral. This is a lot of steps, but once you do enough of these problems, it will make sense. All right. So when you take an integral of this, I get that f of y is equal to, and this is going to be with respect to y, because it's a function of y. And it's going to be, well, y squared. And this is going to be plus c. The reason why this is a regular plus c is because if we look at, the partial of f and integrating it and all that with respect to x, well, notice how f is a function of both x and y, right? And then when you integrate, a function of x and y with respect to only one variable, that's when you have to add, this function term. But when you're only integrating with respect to one variable, like, a lot of times you do, well then you're just going to get a plus c. So notice the difference between integrating with respect to one variable for a multi-variable function compared to integrating with respect to a variable for just a regular old function. And so, well, now that we have f of y, let's just plug it into our thing. So I have x squared y plus 3x, and then f of y, well, that's y squared plus c. And recall that, this is going to be equal to some other constant, right? Because remember that initially, when we started out, this is equal to some constant, right? This is the form that we originally started out with. So this is going to be equal to some other constant. I can call this c1 and then c2. So I just get x squared y plus 3x plus y squared is equal to some big constant, c3. And then if we were given the initial conditions, like x and y is equal to something, we can solve for c3. But you notice how this is the exact same thing that we started out with, right? And so this is how to do these exact total differential problems. Now, when you're doing these type of problems, you have to do something called checking for exactness, okay? Exactness basically tells you the type of solution. So essentially, right, notice how the solution that we kind of ended up with is we have some multivariable function f of x comma y, and that's going to be equal to some constant, right? And so in order for this kind of equation to hold true, right, this describes the solutions of our differential equation, and this only holds true if this is true. Okay, so let me just write it like this. So this is basically the equation to check for exactness. So let's see how you can compute it first, and then we can make sense of this logically. So this is the partial with respect to x, right? So this portion right over here, and now we're going to take it with respect to y. So I guess the partial of this term with respect to y, that's just going to be equal to 2x. And notice how that's equal to the partial derivative with respect to x of this term right over here, right? Because if we take the derivative with respect to x of x squared plus 2y, this 2y is treated as a constant, so you also get 2x. And this tells us that the solution to this is going to be in the form of f of x comma y is equal to c. All right, that's what exactness tells us. If we want to have a surface, right, and the surface is like f of x comma y is equal to c. So for example, right over here in Desmos, I have f of x comma y, and if we want it to equal c, you can do that. But let's just take a look at this original function. All right, to kind of generalize this. Now, if I take a tiny step along the x direction first, and then a tiny step along the y direction, that will yield the same change in height as if I take a step along the y direction first, and then I take a step along the x direction. And that's exactly what this equation is saying. And if you look at the surface, it kind of makes sense why, right? If you take a step along the x direction and then the y direction, that yields the same height as if you take a step along the y direction and then the x direction. I know I'm kind of doing that backwards here. Sorry about that. Right, you take a step along the x direction and then y, that's equal to taking a step along the y direction and then the x, right? It's going to yield the same change in height, right? And so that's just what this exactness is saying. It's saying that in order for this surface to actually be the solution to this equation, that property has to hold up, all right?